Good afternoon, everybody. In this video, we're going to find out the value of acceleration due to gravity at poles considering the spinning of the Earth, considering the rotation of the Earth about its own axis. So, why does the spin has effect onto the Earth? So, in order to understand, let's draw a picture here. So this is the Earth here. This is my x-axis passing through the center of the Earth, and this is my y-axis passing through the poles. And let us consider a point here which makes an angle theta with respect to the x-axis, and this theta we call as a latitude. And depending upon the latitude, the acceleration due to gravity does change. But first, in fact, why does it change? So, if the Earth does not spin at all, then there is only one force acting onto this point, P, which is the weight equals to mg, which is towards the center. But now, as the Earth is spinning about its axis, it also moves into a circle here, this circle here, right? This moves into a circle. Whenever an object moves into a circle, and if you look from the non-inertial frame of reference, there must be a centrifugal force, and this would be the centrifugal force here, the centrifugal force. And the value of centrifugal force, I'll simply write down here, m omega square r cosine theta. That's the value of centrifugal force. So it is clearly, you can see, as the theta changes, the centrifugal force value changes. And at the equator, where the theta is 0 degree, that means the centrifugal force will be maximum. At the pole, the theta is 90 degree, and the centrifugal force will be 0. And exactly for the same reason, the Earth has more radius at the equator and slightly smaller radius at the pole. Why is that? Let me draw it. Draw a picture here. Let's say this is the Earth's surface here. And now, as the Earth is spinning about its axis, there will be a more force, the centrifugal force. Remember this equation, Fc equals to m omega square r cosine theta. So, and if you are at equator, this value would be the maximum, and at the pole, cosine theta will be 90 degree, and the force will be 0. So as there is more force acting on the equator, this is how it looks here. Let me draw a little better. Okay. So it's not exactly okay. So now, why did I draw this way? So if you look at the poles, there is no any force. But if you look at the equator, there is more force acting onto it. So the equator bulges out and the pole remains exactly the same. That means if you look at the radius, the Earth radius is greater at the equator compared to the pole because of the spinning of the Earth. And if in fact it is true for any spinning object. Even if you look at the moon radius will be greater at the equator and it will be slightly smaller at the pole. It doesn't matter Jupiter. If you look at the Jupiter, or in fact, even if you have a spinning toy, and if you spin fast enough, its radius, or it will simply bulge out. Okay. So that is the one point here. Now let's come back here, and because of this spinning of the Earth, the acceleration due to gravity would change, and that's the equation. So in this equation, if you look, this is the acceleration due to gravity, simply by considering the mass and radius of the Earth, and do not considering the spinning of the Earth. If you consider the spin of the Earth too, this is the acceleration due to gravity you will get. And this would be the direction of the apparent acceleration due to the gravity, or this would be the direction of this g prime. So in other words, in this picture, this is the acceleration due to gravity g, and due to the spinning it will be slightly deviated g prime, and we call this angle as alpha. All right. So if you are at the pole, this theta would be 90 degree. So let's plug in. So if I plug in 90 degree, what I get is this value would be exactly equal to 0 as expected. And if I plug in 90 degree here, I'll get alpha to be 90 degree. And this makes perfect sense here, which means the acceleration due to gravity at equator, the spinning of the earth has no effect at the pole. Okay, the spinning of the earth has no effect at the pole. And the value I can simply calculate it by this equation, Gp equals to Gm over Rp square, and this is the radius of the pole, m is the mass of the earth. If you plug in, the value you will get is 9.74 meter per second square. All right, so now let's consider at any other point. Let's consider at theta equals to 45 degree. So here I'm calculating exactly the same thing at 45 degree angle. So at a 45 degree angle, if I plug in into this equation, the value I will get is 9.78 meter per second square. So all I have done is plug in theta equals to 45 in this equation, and I get 9.78. And if you compare the value with respect to 9.81, this value is only 0.02% change compared to the value at the equator. So there is not much effect. All right. And if you calculate the direction of the apparent weight angle, so all you have to do is plug in theta equals to 45 degree in this equation. When I do that, alpha value I would get is 45.01 degree. So what does that tell you? The apparent weight has negligible effect due to the rotation of the earth, or because of the rotation of the earth, the acceleration due to gravity value is very insignificantly affected. There is not much effect. All right, so this was it from this video. So in summary, if I have to summarize, what I can tell you is because of the spinning of the earth, the acceleration due to gravity that changes slightly, and there is only about 0.02% change in acceleration due to gravity at pole due to the or there is no change in acceleration due to gravity at the pole, but there would be change in acceleration due to gravity at the equator. Okay, so this was it from this video. If you have any questions, write to me and I will get back to you. Thank you so much.